Okay, firstly, good afternoon, everybody. I'm delighted to be here to at least give you an insight into some of the research. We only have 15 minutes, so I'll have to be quite quick in both talking and moving through the slides. Just a quick question. How many of you travelled in by tube? Okay, yep. How many by bus? No? Yep, a few. What about cycling, walking? One or two? Okay, good. Car? Yes, that'd be a bit tricky. Getting here right now in car, that would be something. Okay, but let's ask another question. Out of those four options, quick show of hands, how many of you think which option will expose you to the most air pollution? So what about tube? Okay, what about buses? Okay, a few. What about cycling or walking? A few again. What about cars? Okay, one or two, a few. Okay, so you can see that we're all quite confused. We don't really know which mode of transport actually limits the amount of pollution that we're exposed to. But there's a reason for that, and it's partly because we don't really adequately measure pollution with enough resolution to really understand the dynamics for individuals. So just to put pollution into context, it is a global issue. About 10, 15 years ago, 16 of the 20 most polluted cities were in China. More recently, 14 of the most 20 polluted cities are in India. So it's definitely a global phenomenon. And in terms of London, this was something that near the start of my research as a postdoc. This was developed by a model. It's a model of London and the pollution levels. Obviously, red means very, very high. And this is what they hope to be by 2010. Does anybody know what this blob is on the left-hand side, by the way? Heathrow Airport, absolutely. Now, the reality is this didn't improve over that period of time, and it led to a lot of different headlines regarding air pollution, threatenings with fines from the EU, etc. And part of that is because this model was actually built or created based on about 120 sensors to cover about 600 square miles. So there's about 120 fixed air pollution, air quality monitoring sensors throughout London. And you think about that, 120 to cover 600 square miles, about 1 every 5 square miles, is not enough for you to adequately know what the pollution is on your street or even in your local area. So let's just think about pollution, why that might be. Well, first of all, pollution, very rarely can you see it. It's very rare that you see most of the pollutants that we are subjected to. So, for example, you might see a little bit of smog and possibly some aerosols, some particles, if they're big enough. But most of the rest of the pollutants, the sulfur dioxides, nitrogen dioxides, etc., you will not see them. Even these small particulate matter, PM10s and PM2.5s, it basically means the size of them is about either 10 or 2.5 millionths of a meter in diameter, so they're extremely small. And so as a result, we have to find ways of measuring things that you can't actually see. Because if you think of maybe India or China, there's lots of images of the thick smog, so you can clearly see it and there's a problem. But in somewhere like London, you won't necessarily see all that haze. So part of my research was involved in actually using transport, or at least monitoring transport activity, and trying to correlate that with the resultant air quality that's produced locally. And this is all based around urban pollution in cities like London. And the main reason for that is because poor air quality, if you sort of follow the flow chart, shows that it will lead to an adverse health effects and ultimately lead to a social impact in terms of health generally, and also an economic impact in terms of the overall burden on the NHS services, for example. So the project was called MESSAGE. It's actually an acronym. It stands for Mobile Environmental Sensor Systems Across a Grid Environment. Luckily, it spells message, right? But basically, what it meant was that we would develop sensors that you can place on moving platforms like buses and taxis, cars, etc. And then you would then gather all that data. So effectively, what you create is an ad hoc network of sensors that are moving. And then the idea is to develop the infrastructure that will allow you to gather that information and then use that to interpret in real time what the dynamics are of pollution with much more resolution than you're probably you'd get from just modeling a sparse distribution of fixed sensors. I suppose I should mention that it is underpinned by some fundamental science. Just very briefly, when atoms and molecules, which most pollutants are, when they absorb particular wavelengths of frequencies of light, they will become excited. Their states will become excited, and then when they relax back to their natural ground state, they release a photon of energy, and that energy is in the form of a wavelength of light. And by light, I don't just mean the visible light that you can see, but light can be right across the electromagnetic spectrum, and in particular, we worked in the UV range, because that energy range is particularly suitable for monitoring air pollutants. And the result is that what you have is that different pollutants have different signatures in this spectrum. So, for example, this is sulfur dioxide, which seems to have this sort of, all these sharp peaks near, well, this is 200 to 230 nanometers. But again, you've got other pollutants like NO, NO2, benzene, which have completely different profiles. And we use this difference to determine what types of pollutants are in the air and how much of it is there. And how we did that was combining two techniques. My own research background, my PhD, was in atmospheric physics. So we were quite well aware of a technique called DOAS, which is another acronym. But basically, what it does, it uses the sunlight as the source of light. And as that light travels through the atmosphere, different pollutants will absorb, or different chemicals generally, will absorb different frequencies. And then we basically detect the light at the other end, if you like, and compare that to what you started with. And then we use that to then determine how much pollutant is there and how much of it is, what type it is. And the thing about the atmospheric process, DOAS, is that you've got this very long optical path of several kilometers through the atmosphere. And that allows you to pick up very low concentrations of chemicals because they'll give you a stronger signal over a longer path. And then in order to measure air pollutant on the ground, so to speak, we can't be afforded the luxury of measuring over very long path lengths. So we reduce it from, say, a few kilometers to maybe a few meters across a roadside, for example. But in order to keep the sensitivity of the instrument, we then combined it with some techniques from high-energy physics, because they go into high particle collisions, trillions of collisions, and they're looking for just a few hundred sort of signals. And so they're really looking for a weak signal in a noisy background. So by using very robust noise reduction techniques, you can actually reduce the amount of noise in your system. And what that means is that your signal-to-noise ratio remains the same as you go from a long path to a short path unit. And as a result, you keep the sensitivity of your instrument so that you're able to monitor air pollution on trace quantities at very low levels, like parts per billion levels, for example. What this means in practice, in the early research, I mean, if this looks like a violin case, well, it actually is, and that would seem to be the most suitable case to house our unit. And we wanted to replace the capability of, say, a fixed monitoring station. This is a typical fixed monitoring station. Apparently, this is a mobile station. It looks very similar in size, except it's got wheels. But basically, what we wanted to do was then use that same capability, but in a unit that you can carry around, walk around, put it on, cycle in a very sophisticated way, put it to a vehicle, and drive around. And so you can start to map pollutants. I should also mention that there is, before it becomes a sort of a viable product, there is an engineering phase that is involved. So as a scientist, we're quite happy once we can prove the principle that something could work. But an engineer actually makes sure it does work in the environment. So I've got to give credit to the engineers as well. What this means is that you can generate maps. So this is around the campus of Imperial College. That's actually the Royal Albert Hall there. And this is when we did a few circuits around and then actually aggregated the data to get an understanding of where the key pollution sort of levels peak. And you can see they sort of peak at the junctions, which is probably understandable because you've got more traffic in both directions. We've done similar exercises. For example, we put a unit on a longboat and took it all the way from West London right across East London. And again, mapping for different pollutants, and you can see the heights represent where the sort of elevated levels are. And this type of visibility, you wouldn't get that level of resolution with the current fixed set of monitoring stations. Another interesting sort of investigation we did, we drove a sensor or a vehicle and monitored pollution from sort of South London all the way through to Earl's Court. And we actually identified at the time 2 potential pollution hotspots. One was across Vauxhall Bridge, That may be understandable if you've been in that region. There's lots of multiple lanes of traffic in either directions. But this one is quite interesting because at the time, the hotspot was identified near Harrods and Harvey Nichols. And that poses some interesting questions for society. Let's suppose, and I'm not saying it is, but let's suppose there really was a permanent pollution hotspot near Harvey Nichols and Harrods. What sort of information would the authorities feel was adequate to release to society? And these are discussions which you have to think about because they can affect things like, I don't know, house prices, for example. If you've got young children, that dream penthouse that you wanted in Knightsbridge, it may not seem as attractive anymore, for example. So these are things which you may want to, which, if you like, the powers that be have to consider. Another example of how pollution can vary quite considerably. So if we take the sort of legal limit, roughly, is about 100 parts per billion. So it's down here somewhere. But this is where we went on we took 2 units, we were walking side by side with them, and you can see initially they follow a very similar trend. But at this stage, one decided to stay at roadside or curbside, the other one was in the central reservation of a busy main road, and you can see there's a huge spike in the middle of the road as opposed to on the sidewalk. So going back to the question about which mode of transport are you more subjected to? Well, it depends. I mean, technically, if you're in the middle of the road, which you are if you're in a car, you may well be subjected to much more pollution than if you were at the side of the road. This is another quick example of pollution spikes near traffic lights. So these spikes represent the pulsing of traffic lights and the engines revving up as they drive off. And again, you can see you've got some very high spikes, and the body has a non-linear response to pollution spikes. So in other words, being exposed to a high dosage over a very short period of time is far more damaging than being exposed to, say, the same dosage but spread out over a longer period of time. So again, it makes certain jobs, if you like, I don't know, selling flowers on a street corner or newspapers, actually could be quite dangerous, and especially if you've got respiratory issues. So that's about one sensor, and one sensor can do quite a lot, but the real aim, I'd almost compare it to, for example, whoever, designing the first PC. A PC in itself can do a huge amount, but if you have a complete IT infrastructure, then you can do a lot more. And that's really where the key areas of the research are. So this is a scenario around East London, and basically we've got about 140, 150 sensors. This is based on a scenario, so they weren't real sensors deployed, but we said, imagine if we had deployed sensors in this nice fixed sort of Manhattan grid style, what would the data look like if it was monitoring continuously? And you'd get something, oops, what's happened here? Okay. So you get something like this, for example. During the morning, the main sort of arteries, the main road arteries are pretty polluted. And then as rush hour starts to die down, these arteries, these pollution levels start to fall. You may find pockets of pollution in different areas. And this is a type of visibility that would be really useful for local authorities, okay? Because then they can make real-time decisions like rerouting traffic and limiting the impact on human health. And also you could do things like analyze the impact of the school run on the local air quality around the school. In this particular snapshot, it kind of demonstrates that the school run actually does impact on the local pollution. So at 3:30, it's still polluted, and it's outside of rush hour, for example. And so these are the types of details that we really like. We've also done studies, for example, we did a project in Brighton where we covered 3 primary schools which were located near to main roads. We monitored the pollution from the main road and the emissions from vehicles as they drove past, but we also simultaneously monitored pollution within the school grounds itself to see what the correlations are. Again, it's no surprise, and it's quite interesting that a few years later we had headlines like this in London, where they now identify that locating schools right next to main roads is probably not the best idea, especially because many young people have respiratory issues. So in terms of the research, the real challenge now is really, well, okay, it's not really realistic to deploy 150 sensors to that level of density in a part of London. But the question is, what happens if we could replace these sensors with maybe fewer moving sensors? And then could we still get the same level of of detail, the same level of interpretation from fewer moving sensors, because that, of course, will be much more cost efficient. So how we approach that, we say took the original 140 sensors and then initially said, well, let's assume now that we've got 7 sensors that move in this sort of cyclical cycle, and then look what the data will produce and compare that to what we had originally. And then we make more complicated irregular paths. And then finally we sort of said, well, let's tap into the bus network and assume that we had them fixed to buses so that now the routes are only limited by the bus network. And what you end up with is, this is the original plot that you would have seen from a fixed sort of data, fixed grid of sensors. And this is the data from the mobile sensors. And this is the difference between the two. In other words, it's sort of highlighting what information is missing. And you can see there's very little. So it gives us great hope that we can actually use mobile sensing to actually generate these pollution maps by using intelligent sort of sampling and reconstructing the data with fewer sample points. And that's really where the research has led to at this present day. I should also mention a couple of other benefits of research, one of which is innovation. So in fact, even though we did most of our research based on air quality monitoring, in fact, what we created was a multi-species gas analyzer, like a platform that can analyze lots of different types of chemicals in the air. And so what you find is that different industries may have an interest in different types of chemicals. So, for example, the oil and gas industry, they're quite interested in hydrogen sulfide because it can lead to cracking of pipelines and so on. So again, our units are able to use the same technique and tailor it towards monitoring for hydrogen sulfide. And there's lots of other areas, for example, defense might look for biohazards and so on. So that's one benefit of fundamental research, I would say, is that it can lead to innovation in many different areas. It's a platform technology. And the other benefit, which might be less surprising, is creativity. So in fact, I would argue that if you have a creative pursuit, you could actually use your technical knowledge to enhance what you do creatively. So a personal example, for many years I was a part-time DJ, known as DJ Chemist, fair enough. But the thing that I used to like was remixing. So hopefully maybe you know what a remix is, where you take elements of one track, you take elements of another track and you fuse them together and hopefully create something that sounds fresh and cool and hopefully better than the originals. Now, in order to do that, what you're really doing is combining audio wave files in a particular way and making sure they fit in a certain way. And when a lot of the remixing went digital, I actually realized that I was almost doing the opposite of what I was doing in my research, where we were taking light waves and effectively disentangling them so that we could find out the sort of contributions from all the different chemicals. So you're sort of breaking apart light waves into its separate components, whereas with a remix, you're combining separate components, albeit sound waves. So what it meant in practice, I found that you could really push the envelope in terms of what sort of genres you can fuse together. So I sort of used my technical know-how, if you like, to push and stretch the limits in terms of what sorts of things you can remix. Now, in the interest of time, I can't actually play you anything. However, you can check out DJ Chemist on SoundCloud, and there are plenty of tracks that you can enjoy at your own pleasure. So, just to summarize this particular segment, mobile sensing, it does have the power to really give you the visibility that you need. I mean, a lot of the legal averages are based over hours of data, 24 hours, but of course we breathe in every few seconds. So we want to know much more about the dynamics. Also, whilst you may have the general trend of what the pollution level is in your general area, you actually want to know what you personally are exposed to. And mobile sensing certainly offers that capability. And you can capture most of the trends that you would have captured with a fixed, dense network. And then the other thing is, I suppose, is that in order to change policy, because ultimately you want local authorities to adopt this type of methodology, but they are not going to do that unless effectively they are mandated to do that, because they don't have a spare budget to buy lots of monitoring equipment. And so they are influenced by what the legal requirements are. And the legal requirements, they say it's based on best available technology, but often it lags behind the technological development. And the only thing that moves things forward is often public concern. and so that the policymakers, or politicians if you like, actually start to take note. So I would bear that in mind. And then on a personal level, my only research interests, for any of the youngsters amongst us who were maybe thinking of going in a career in research, I started off as an undergraduate chemist, and then I did a PhD in physics, and then in terms of research, pretty much nowadays it's more maths and computing and modelling of sensors and not so much on the instrumentation. So research is a really good career to sort of evolve into many different fields. And then finally, I'd say to tackle global challenges like air pollution, you actually need elements of what I've called three things, conveniently condensed into an acronym, ICE, which is innovation, creativity, and enterprise. And if you combine those in the right way, then I think we can tackle most global challenges. And it also means that there's always something for somebody to get involved in. So, thank you for listening. And yes, any questions, I'm happy to field them. Okay.
You asked at the beginning, which way of transport might be the most polluted, but then you didn't mention the tube. So how's the tube with air quality?
Well, I'll be honest with you, there is very little pollution monitoring on the tube itself. We monitored lots of things, but we didn't really get to the stage where we did much research on pollution in the tubes. But if you think about it, the tube itself, where does it get its air from? It's not fresh, clean air coming from somewhere, so it's going to be, and also it's probably going to be less likely to dissipate. So in theory, the tubes could be just as polluted as anywhere else, but it doesn't require more research. And as I said, my main focus was to develop the capability of doing that, but to enable other groups, interested groups, to actually start looking into those areas. Okay, there's a question at the back.
Comment and a question. My comment is my group in Cambridge, we actually have a SoundCloud song called Super Photons.
Excellent.
So I think other people also do music. And my question is, how long does it actually take, or do you actually get your research implemented into policies?
Right, well, so in terms of, and it's a good question, I think the short answer is it takes a long time to change legislation, even if you have the technology and you prove that it can work. So part of my research involved commercializing the technology. So I'm co-founder of a business, technology business called Duvas Technologies. And at that time, when it was first formed, probably nearly 10 years ago, I was tasked as the business development, and I spoke to lots of local authorities and interested parties both home and abroad. And what I found is that local authorities, whilst they buy into the vision, and those on the ground in the environmental section would love to have this equipment, whenever it came to applying for budgets and so on, and applying for funding, the message would be, well, we're not mandated to do it. So, apart from it's a nice thing to do, there's nothing more that forces local authorities to start prioritizing these areas. So the way how it works, you have to influence the air quality expert group, and then they hopefully will influence the legislators who will then change policy. But what really makes a big difference is when there is an increase in level of public concern. And that has happened over the years. When I started this pollution research 10 to 15 years ago, it really wasn't something that captured the public's sort of, I wouldn't say imagination, because that makes it sound grand, but it didn't really capture the public in the way that it does now. Now, if you go on Google and put air pollution in the news, you will see lots and lots of different types of articles. So I'm hoping that legislation will now finally catch up with technology, and maybe the business will sell a few units. Luckily, as I said, it's a global phenomenon, so there is lots of uptake in other parts of the world where perhaps it's not so bureaucratic, for example. Okay. Yeah, there's a question there.
When you were comparing your static sensors with your mobile ones, you did different pathways. Did you find like an optimum pathway?
Absolutely. Yeah, it's a good question. So when we was looking at the different scenarios for the moving sensors, what we was trying to establish, so we took, if you like, the fixed grid as our standard to say this is ideally the type of information we would like to see. But then we generated new sets based on moving sensors and saying, well, what would they measure if they were moving in a particular way? And what we found was that, in fact, an ad hoc network, you lose very little of the key information. However, it is always useful to supplement that with a small number of fixed stations. So in fact, the current existing monitoring stations, we're not sort of advocating we replace them. It's just that we can now augment what we already know and also validate often what the models predict by actually being able to measure much more specifically in terms of time and space. Okay. Oh, I think there's a question there.
Thank you. I was wondering what's the current cost of a mobile sensor, and are there any plans to make them more affordable?
Right, okay. So the current, I can't say the current cost, but the units that we developed are of the order of several £1,000s each. Okay, but just to put that into context, at the time, the fixed stations, those fixed units that look like sheds, they were about £120,000 to construct. Since then, there has been development in pollution sensing, not just by our own company, Duvas Technologies, but other entities. The issue is, it depends on what technique you use. So you can get some very cheap sensors, but they won't be as accurate. So it's almost like you want something fast, accurate, and cheap, and you can always only get 2 out of the 3. And so we went for accuracy and you know, fast, sort of high throughput, which inevitably means it's going to be slightly more expensive than maybe going for something less accurate. Okay, a couple more. Yeah, sure.
I'll go first if that's so kind of following on from her question, the current sensor's the size of a violin case, which is obviously pretty remarkable on a car, maybe less noticeable on a bus.
Yeah.
But you said that ad hoc networks are the best. Do you think that they might be miniaturized, made even smaller in the future?
I think they probably will, but there are some limiting factors. I mean, you notice that we're using a technique which originally relied on a huge path length of, as I said, several kilometers. And every time you reduce that path length, so if you reduce your path length from several kilometers to, say, several meters, you're reducing the strength of your signal by a factor of 1,000. So it's only because we employed some very robust noise reduction techniques, which were developed in high-energy physics, and applied them to this particular unit, that we're able to keep the sensitivity. So the limits are that if you go to shorter and shorter paths using an optical technique, then in fact you're going to lose the sensitivity. And because you're monitoring pollution, unless it's extremely high, you want to monitor ambient levels as well as when they, you know, exceed. So I think there are, they will get smaller. Technology always tries to make things smaller and faster, but I don't think it's just simply a case of, you know, as chips get smaller, the units themselves will get smaller, because there are some hard limits in terms of the setup. You can use other techniques, as I said, chemical techniques, for example, but then the problem with them is that they have to be stationary for several minutes before you can start measuring. So therefore, having a chemical measuring technique on the move means that it's never stationary, which means it wouldn't be accurate again. So there are these trade-offs, but I believe they will get smaller, and ultimately, you know, the dream would be that, you know, all of us would have one somewhere, either on our phone as a sensor or something you could wear, and then use all that metadata to create this large network so that we really get a good understanding of the dynamics in real time. But I think we're still a little way off, although I did notice the mayor had put some funding into having schools, school children come into school with backpacks and with pollution monitoring sensors on them, and then start to monitor the different routes in which they come into school and what they were exposed to. So going back to our original question, maybe it will be answered by school children in due course. Okay, well, thanks again. Thanks for your time.